In this unit, you guys have been looking at Coulomb's law, and Coulomb's law is just a law that tells us how the forces of two charges interact because of the charge. So if I have charge particle Q1 and charge particle Q2, there's a couple different things that could happen, and it depends on if these charges have the same charge or if they have opposite charges. If they have the same charge, then the force will be a repulsive force, and we'll have the situation where the two want to move apart. If they have opposite charges, then we'll get the opposite case. So we have the two charges here, and if Q1 and Q2 have opposite charge, then it's an attractive force. So the electric force can go either way. Now what Coulomb's law says is it says, well, how strong is that force, and what does it depend on? It depends on two things. It depends on the size of the charges, and it also depends on how far apart the charges are. We call that distance the distance r. So Coulomb's law is summarized by F equals Q1 times Q2 divided by r squared times k. And so it's an inverse square law, that it's inversely proportional to the square of the distance. It is directly proportional to the charge of the objects. If you double one charge, you double the force. If you double both charges, you quadruple the force. If you cut the distance in half, you quadruple the force. So remember how the inverse square law works. Now this constant k has been experimentally found and measured to be 9 times 10 to the ninth Newton meters squared per Coulomb squared, which is a fairly large number. Okay, now, this law should actually look sort of familiar to you, because the law of universal gravitation says that the force one massive object exerts on a second massive object, called gravity, is proportional to the inverse square of the distance and the masses of the two objects times the gravitational constant g. Now k is 9 times 10 to the ninth Newton meter squared per Coulomb squared. G, if you remember, is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Okay? You'll notice this is a very much smaller constant than k. So masses have to be huge in order for us to have a detectable gravitational field. Charges don't have to be so big for us to be able to detect them. And so oftentimes you will be dealing with microcoulombs, that's times 10 to the negative 6, or nanocoulombs, that's times 10 to the negative ninth. So a coulomb of charge is actually quite a bit of charge.